All right, let's do an example. Here's a big, long write-up about how carbon dating works. Okay, so carbon-14 is a specific isotope that's in all living things. That's its half-life, 5,370 years. Okay, all living things have like a constant amount of carbon-14, but once they die, the carbon-14 starts to break down. Okay, so if we analyze something that was once living and determine how much carbon-14 is remaining, we can find its age just with math. So examples of things that can be dated using carbon dating just had to be alive at once. So a bone or a wooden tool or leather. By doing carbon-14 analysis, you'll determine if it's a wooden tool when the tree was cut down or when the branch was broken off. For leather, when the animal was killed. For a bone, when the animal or person died. I hope that makes sense. It's pretty interesting. Okay, so I'm going to come at you with a couple of examples. So let's determine the percentage of carbon-14 remaining after 100 years of this living sample being killed. Here's how we set it up. Remember, it's a percentage, so the starting amount is 100. I'm going to be able to do this just by putting in the numbers. All right, so this is my time, 100 years. This is my half-life. Maybe I should write the original formula just so we see what's going on. Okay, so the starting amount, 100%. Okay, it's always 0.5 in brackets. And then time divided by half-life is the exponent. The units have to match, and it's all good. It's 100 years here. It was 5,370 years here. Okay, if we put this into our calculator, just the way we wrote it down, it should work. But your exponent will have to be in brackets. Okay, that looks good. And we get 98.7%, which makes sense because 50% of the sample will be gone after over 5,000 years, and we're just waited 100 years. Okay, so carbon-14 is particularly useful for things that are really old. Okay, let's get to a new example here. I want us to actually date something now. So I'm saying a wooden artifact contains 75% of its original carbon-14. We're going to determine its age. Okay, to figure it out using this formula would require some math I don't really want to do. I'm going to just show us how to do it with our calculator. Okay, the age is time. That's going to be an x value. Okay, so it's t in the formula. When we graph it, it'll be y equals this stuff times x over the half-life. When we're finding an x value, I just want to remind you, is it trace or intersect? It's intersect when you're finding an x value. Okay, so I'm going to show us how to do it. We got to graph our formula. Oops, I got some old stuff in there I'll get rid of for you. Okay, so our formula is going to be 100 times 0.5 to the power. Make sure your exponent is in brackets here. It's going to be x, the time, divided by the half-life, 5,730. We're doing an intersect when 75% is remaining, so y2 is going to be 75. Okay, I already know like my window settings have to be changed because we're dealing with thousands of years essentially. I'm not sure what they are now, but let's have a look. Okay, so x goes from 0 to 30 for me, but x is the age. Let's go up to at least a half-life, 5,730. Okay, we won't need to go to a full half-life because 5,730, there'd be 50% left, but we have more than that, so it's going to be less than 5,730 years, so this should be fine. Y min, y is the percentage remaining, so you don't have to go above 100. It's going to start at 100 and go down. 0 to 100, that's going to be just fine. Let's see what it looks like. Okay, so that represents the carbon decaying. That's the 75% line. If we just do intersect now, This is one, ooh, it started close. I'm just going to hit enter 3 times. We'll get our answer very quickly. It's going to be 2,378, I'll say 0.2 years. Looks good.